The model runs perfectly on your laptop. The benchmarks pass staging with 0 errors. Then the first wave of real traffic hits production, and the entire system buckles. The symptoms are immediate. Latency climbs to seconds, users abandon the application, and inference costs explode. Engineers will typically spend the next 2 weeks chasing optimizations that have nothing to do with the model's weights. They fail because they operate under the assumption that latency and throughput are the same metric. Look at these 2 parallel data flows. Batching multiple requests at the system level improves throughput, meaning the hardware processes more total requests per second. But it penalizes single request latency, because the first request in the batch must wait for the others to arrive before processing even begins. Closing the gap between a functioning model and a system that can survive real traffic requires abandoning blind optimization. You have to build a strict diagnostic framework first. Grabbing a checklist of generic optimizations and applying them without diagnosing your underlying hardware constraint guarantees you will spend weeks optimizing a bottleneck that doesn't exist. We have to start with the physical constraints of a GPU. There is a massive discrepancy between the sheer processing power of the compute cores and the limited bandwidth of the high bandwidth memory, or VRAM, that surrounds them. An LLM inference call happens in 2 distinct phases. The first is prefill. This phase dictates your time to first token, or TTFT, how long a user stares at a blank screen before the model begins to answer. During prefill, the model processes the entire input prompt at once. It loads the weights once and runs the prompt through every layer in parallel. Because it executes everything simultaneously, prefill is bottlenecked exclusively by the GPU's compute cores. The second phase is decode, which governs your time per output token, or TPOT. This determines whether the generated text streams rapidly or feels sluggish. This timeline illustrates the difference. After the parallel prefill block on the left, decode generates output tokens sequentially. For every single new token produced, the system must load massive weight matrices from VRAM all over again. Zooming in on the right side of the process, you can see the actual physical bottleneck. The math required to generate a single token is negligible, but the physical data movement is enormous. This renders the decode phase severely memory-bound. Because prefill relies on compute and decode relies on memory bandwidth, they stress entirely different physical components. An optimization technique that accelerates one will do absolutely nothing for the other. If your time per output token is too high, you have a memory bottleneck. The engineering objective is simple: reduce the physical volume of data moving across the GPU. This geometric structure represents the baseline fix, quantization. By shrinking model weights from a standard 16-bit floating point format down to a 4-bit representation, you cut the memory footprint by a factor of 4. With a footprint that small, the memory-bound decode phase accelerates instantly. You are requiring significantly less bandwidth per generated token. Another angle of attack is speculative decoding, a technique designed to hack the sequential one-by-one nature of token generation. Watch this mechanism in action. A small draft model rapidly predicts a sequence of tokens. Then, a massive large model sweeps over all of them, verifying the entire sequence simultaneously in a single parallel forward pass. The ultimate, if psychologically difficult, method of data reduction is model compression. Engineers often default to massive 70 billion parameter models when a highly tinned, distilled 3 billion parameter model would execute the specific task at a fraction of the hardware cost. Resolving a high time per output token requires minimizing physical data transport across the hardware, regardless of the model's internal complexity. If the time to first token is the problem, the bottleneck shifts to the compute-bound prefill phase. The primary culprit here is the inherent inefficiency inside standard attention mechanisms. During long context sequences, standard attention computations are incredibly wasteful. They constantly shuttle intermediate matrices back and forth to the slower VRAM, leaving the compute cores starved for data. This memory hierarchy diagram shows the solution: FlashAttention. It breaks the data down into tiny tiles that bypass the VRAM entirely, slotting perfectly into the GPU's ultra-fast onboard SRAM to complete the math uninterrupted. Optimizing the math in SRAM is highly effective, but bypassing the math entirely through caching is even better. Request-level caching via Redis serves exact input matches instantly. A layer beneath that, semantic caching uses embeddings to evaluate query similarity, returning cached answers for conceptually identical prompts without touching the model. For deep, repeated system prompts, you apply prompt caching. By saving the key value computations of a static prompt on the first pass, you eliminate redundant prefill work on all subsequent requests, driving your time-to-first token down significantly. Crushing a time-to-first token bottleneck requires treating every mathematical operation as a liability. You either optimize its physical execution inside the SRAM, or you cache it so you never have to do it at all. Even with perfectly optimized prefill and decode speeds, an LLM in production faces a system-level threat: concurrent user traffic. Without careful memory allocation, the queue collapses and latency spikes. The baseline defense is the KV cache. It stores the key and value matrices of past tokens, so the GPU never has to recompute them to generate the next word. Look at this representation of GPU memory to see the flaw in a naive KV cache. It reserves massive continuous memory blocks sized for the maximum possible context length. A short request enters, leaving 90% of it empty, but completely locked. Upgrading to PagedAttention fixes this. The rigid blocks dissolve, breaking memory down into dynamic 16-token pages that are allocated strictly as the sequence grows. By reclaiming that wasted idle space, dynamic allocation allows the exact same physical hardware to serve up to 4 times more concurrent requests. You pair this memory efficiency with continuous batching. Instead of processing rigid groups of requests and waiting for the longest one to finish, the batch becomes a moving pool. The millisecond a short request finishes, a new request takes its slot. Finally, you optimize the external serving path itself. Using gRPC protocols cuts serialization overhead, and streaming tokens directly to the interface manipulates perceived latency, making the response feel instant to the user. System-level throughput techniques do not make a single forward pass run any faster. They exist solely to prevent the hardware's memory layout from becoming a bottleneck at scale. Writing low-level CUDA code is rarely the job of a modern AI engineer. The actual work is matching precise symptoms from production to the correct architectural lever. This diagnostic matrix organizes the logic. High time to first token means a compute bottleneck during prefill. You must deploy prompt caching and FlashAttention. If your time per output token is high, you have a memory bandwidth bottleneck during decode. You execute quantization and implement speculative decoding. If your throughput collapses under load, you have a capacity bottleneck in the queue. You activate PagedAttention and continuous batching. You don't have to build these techniques from scratch. Modern inference engines like VLM and TensorTLM ship with these complexities bundled and waiting to be toggled. Senior AI engineering requires the diagnostic mental model to identify a specific system failure and flip the correct architectural switch in production.